Welcome to my set of tutorials covering RISC assembly language. This series discusses the RISC-V processor, covering 32-bit and 64-bit systems supporting floating point and vector extensions. There will be additional tutorials covering ARM. Part 1. RISC-V architecture. The design of RISC-V uses a reduced instruction set computer (RISC) architecture. RISC-V originated in 2010 as a project at the University of California, Berkeley. The suffix V indicates that it is the fifth generation. RISC technology design uses less instructions, and consequently features a smaller processor die size. This means lower power consumption, making it ideal for use in embedded systems. RISC-V is now under the stewardship of RISC-V International, based in Switzerland. A distinguishing feature is that it is open and royalty-free. Implementations use a naming convention to denote which instruction set architectures, ISA, are available within a specific implementation. An example being RV64I or RV32E, which stands for RISC-V with a 64-bit integer instruction set and RISC-V with a 32-bit reduced integer set, respectively. The integer and reduced integer designations form the base integer ISA. This is mandatory for implementations. Optional extensions are defined as M for integer multiplication and division. Here the designation RV64IM would mean 64-bit with integer and integer multiplication, division support. A for atomic extensions. F and D for single and double precision floating point. C for compressed instructions. E for embedded. There is also the ability to support non-standard extensions. Currently there are 4 separate base ISAs with work on a 128-bit 128i implementation. A summary of the base integer instruction set variants is RV32i, RV64i, RV32e, RV64e. Registers are locations that store values. They are similar to variables in high-level languages. The primary way of interfacing with the RISC-V system is via the register set. Generically, the registers may be referred to as RD, destination register, RS1, first source register, and RS2, second source register. Registers are denoted by their application binary interface, ABI name, to make it more convenient to the coder. This is like high-level languages where variables are given meaningful descriptive names. There are 32 unprivileged integer X registers whose width is determined by the instruction set, which is either 32, 64 or 128 bits. As mentioned earlier, the registers have alias names which reflect their usage, such as X1, known as the RA register, which holds the return address. The alias names are referred to as the application binary interface ABI register name. Even though the registers are general purpose, the alias name function should be respected. For example, the saved and temporary registers are used for functions where the coder knows when to save registers prior to making the call and when they do not need to. When the programmer calls a routine, this routine is termed the calling routine, and the routine that is being called is the callee routine. The temporary registers, T0 through T6, are saved by the caller, and the saved registers, S0 through S11, are saved by the callee. So, if the caller was not using register T1, then it would not be necessary to save it prior to involving the call. The program counter, PC, keeps track of program execution and is not used as a general-purpose register. The term xlen refers to the data width 32, 64 or 128 bits. Note that RV32E and RV64E have 16 registers. The non-contiguous register layout is for consistency between register sets. There are also 32 floating point registers that are accessible to the programmer in floating point capable processors. The instructions are 32 bits wide. The general format of an instruction is to include common fields such as a destination register, one or more source operands, an operation code known as an opcode, a function field such as 3-bit, funct3, and 7-bit, funct7, which defines a particular operation. Immediate, which is a constant value such as hexadecimal 5F. There are 4 base instruction formats known as I-type, R-type, S-type, U-type. In addition, there are 2 variants of the I-type instruction known as B-type and J-type. These instructions use conditional and unconditional branches respectively, to alter program flow. The immediate fields are used to encode the branch destination. Conditional branches depend on whether certain program events have occurred. An example could be a decrementing counter, where a branch in the program logic only occurs if the counter has reached value 0. An unconditional branch happens regardless of conditions. An example might be a jump to an interrupt handler service routine if a critical or non-critical event was encountered. I-type instruction. Most of the fields occupy the same bit positions across instructions. An example is the instruction add IA1. A1. 1, which disassembles to hexadecimal 00158593. The breakdown of the fields for this instruction is shown in the diagram. The add I instruction format is termed I-type for immediate. The instruction adds the contents of register A1 plus a constant of 1 to register A1, so the effect is to increase the value of A1 by 1. The A1 register in both the RD and RS1 fields corresponds to the value hexadecimal B, which is the 11th X register, so although the programmer uses the more friendly register name, the machine code still uses the X register number. R-type instruction. The next instruction, add T3, T1, T2 is an R-type instruction as it uses the registers for both operands. Register T2 is added to register T1 and the result is placed in register T3. Disassembling the instruction produces the machine code hexadecimal 00730E33. The field breakdown is S-type instruction. The store word instruction, SW, uses a register and an offset to calculate the destination address. No destination register is involved since the destination is memory. The instruction stores the 32 bits held in register T0 into the memory location pointed to by register T1 plus an immediate offset of 0. The format of the S-type instruction is as shown. Note that the immediate data is broken down into 2 separate fields with the lower 5 bits replacing the unused, in this type of instruction, destination, RD, field. Disassembly produces the hexadecimal machine code 00532023. U-type instruction. The U-type format is used by 2 instructions, LUI and AUIPC. There are 20 bits in the immediate field which permit a larger range of immediate data. These 20 bits represent immediate bits 31 through 12 with bits 11 through 0 having the value of 0. It is possible to visualize this as loading bits 19 through 0 and then shifting the bits 12 places to the left, which helps works out the immediate bit settings. AUIPC then will take a 20-bit immediate value, shift this value 12 places to the left and add it to the value held in the program counter. This result is placed in a destination. To take a specific example, assume that the program counter has a current value of hexadecimal 100B0, the instruction AUIPC, T0, hexadecimal 5A5A5 will add hexadecimal 5A5A5000, which is the shifted immediate value, to hexadecimal 100B0. Loading hexadecimal 5A5B50B0 into register T0. LUI adds the 12 place, left shifted immediate value into the upper immediate 20 bits of the destination and zeroes out the lower 12 bits. It can be combined with another I-type instruction to form a full 32-bit address. LUI contributes address bits 31 through 12 and the regular I-type 12-bit immediate instruction provides bits 11 through 0. LUI example. The instruction LUI T1 0x5A5A5 will add the immediate data 0x5 of 5 of 5000 to register T1. To generate a full 32-bit address, use a 12-bit I-type instruction to provide the lower 12 bits. Even though the instruction format and use of GDB will not be covered in more detail until tutorial 2 of this series, it should be possible to follow the GDB trace shown here. The trace shows the contents of register T0 and T1 after the ADDI instruction has been completed. Load immediate, LI. Instead of using the two instructions shown above, the code using LI looks like LI T1, hexadecimal 1234006. This pseudo instruction could be translated into LUI T1, hexadecimal 01234. ADDW T1, 6. Note that pseudo instructions are automatically translated by the assembler to one or more real machine instructions. B-type instruction. The B-type instruction is used with conditional branches. With this instruction, the immediate field has a range of 13 bits. This is achieved by setting the least significant bit to be 0 and then substituting its bit position with bit 11 in the immediate field IMM, bits for through 1. In the code fragment, the location of the label putet is at address hexadecimal 100F8 and the branch instruction is located at address hexadecimal 10104. Since this is a backwards pointing branch, the immediate field is a minus value. Converting it using 2's complement gives a value of hexadecimal C or 12 places back. J-type instruction. Unconditional branches use the jump and link instruction, JAL. This is a J-type instruction. It is similar to the B-type instruction with the immediate bits in disjoint fields to allow for more efficient decoding. In this example, a JAL instruction is encountered at program counter address hexadecimal 100C0 and the instruction points to a label located at hexadecimal 100D4. The number of bytes to jump is encoded in the immediate bits. The machine code produced is hexadecimal 01400F. The opcode for the instruction is hexadecimal 6F and the destination register is X1, which is the return address register, RA. There is an aliased instruction J which uses the 0 register, X0, instead of the RA register as shown below. The aliased instruction J hexadecimal 100B8Q is encoded as JAL0, hexadecimal 100B8Q. Note that register X0 is read-only, holding the value 0. Additional information, opcodes, and function fields. The opcode field can be the same for different related instructions. The opcode is 7 bits wide, occupying bit positions 6 through 0. To take a specific example, the binary opcode 01100011, which is hexadecimal 33, refers to R-type integer arithmetic and logical instructions. Each of these instructions are differentiated by the funct3 and funct7 fields. The numerical suffix refers to the number of bits used. Funct3 is a 3-bit field and funct7 is a 7-bit field. This is really a 10-bit field broken up into 2 subfields. It is non-contiguous to ensure consistency across the different types of instructions. This aids decoding, and avoids waste by reusing the bits for different purposes, when a function field is not required for that particular instruction type. The type of instruction defines which funct field is in use. The funct3 field will always occupy bits 14 through 12 on any instruction that uses the field, and funct7, used on the R-type instruction, will occupy bit positions 31 through 25. The U and J-type instructions do not use the funct fields and instead will use these bits to specify a greater range of immediate bits. Think of the opcode as being the instruction category, and the funct field as a related operation within that category. The table shows which of the funct fields are used with each instruction type. This table shows how some arithmetic, logic R-type instructions are defined. We have reached the end of this tutorial. Even though the runtime was short, it is expected that approximately 1 hour is needed to pause the video and study the material comprehensively. Tutorial 2 of this series covers simulation, emulation and cross-compiling. Currently there are low-cost hardware implementations on the market, but emulators are often used in professional environments. Barebones, embedded system programming does not rely on an existing operating system, so this section will be of interest to developers working in this environment.
We have covered the basic architecture of RISC-V with a bitfield breakdown of I-type and R-type instructions. R types can be recognized by the number of source registers. The jump and branch instructions will have a dedicated tutorial. The next tutorial will cover emulation and simulation. Cross-compilation is discussed, which allows development on non-native systems. Again, many thanks for watching. Freely downloadable links to these tutorials and companion PDF books can be found at my website risccomputing.com. See you in tutorial 2.